Let's talk about experimental design. So this is lesson 3.5. So most experiments feature a completely randomized design. So treatments are assigned to experimental units at random. For example, a company wants to test the effectiveness of a new mosquito repellent. They recruit 120 volunteers. 40 of them get the new repellent, 40 of them get the old repellent, and 40 of them get no repellent. Each volunteer is then put in an area that's very active with mosquitoes for 30 minutes, and then their bites are counted. So 120 volunteers, that's the experimental units. We split them into no repellent, old repellent, and new repellent. That's the treatments. There's 3 treatments. And then we look at the response. We compare the different responses. So replication, each group is sufficiently large enough. They are randomly assigned. And yeah, there's at least 3 groups. So this is a well-designed experiment. Now, what if there's some kind of variable that we know skews the results? So for example, what if people with type O blood tend to attract twice as many mosquitoes as people with type A blood? So in a completely randomized design, one group might randomly have significantly more people of a certain blood type than another group. So to account for that, we might consider doing a randomized block design, isolating the variable by what we call blocking. Blocking is kind of like stratifying. So blocking ensures that the beginning of the experiment, the units within each block are similar to one another with respect to at least one blocking variable. So what would that look like? So we start with the same 120 volunteers, but we take the 48 volunteers that have type O blood, and then the 72 volunteers that have another type of blood. And then within each block, we split it into a third, a third, a third, give each of them the treatment. Second block, a third, a third, a third. And then we compare the results within the first block, compare the results within the second block, and then compare everything else. So another example might be if we know that men and women react differently to something, we would separate the experiment at the very beginning into men and women, and then do the random assignment within the men, random assignment within the women. That way you don't accidentally end up with a group where it's like 8 men and 2 women have one of the treatments, and we know that it affects them differently. So a special type of randomized block design, it's called matched pair, where the subjects are arranged in pairs. So that's key. Matched pair design has pairs. Makes sense. With each pair, one subject gets randomly assigned one treatment and the other gets assigned the other treatment. So an example of that is a bicycle company wants to test a new tire. It recruits 40 volunteers from a local cycling club and asks them to put the older model tire on one wheel and the new model tire on another wheel. Whether the new model goes on the front or the back is randomly assigned. After 4 weeks, the wear and tear on the tires is measured. The 2 tires are called a matched pair. Now, sometimes a matched pair might be one unit gets both treatments, one after the other. So for example, a class might decide to see whether doing sit-ups or jumping jacks elevates the heart rate more. For those of you taking IB Bio for an internal assessment, you can do something like that. Thus, everyone in the class gets their baseline heart rate measured. They flip a coin, and if it comes up heads, they do the sit-ups for 30 seconds and get the heart rate measured, and then they rest. Then they repeat with jumping jacks. If a coin comes up tails, they do the jumping jacks first, recover, and then do the sit-up. So here the matched pair is the person itself, and the 2 treatments are which exercise you do first, the order being randomly assigned. Now, finally, let's look at single blind and double blind studies. In a single blind experiment, either the researcher or the subject doesn't know what treatment was assigned. In a double blind experiment, both the researcher and the subjects don't know what treatment was assigned. And double blind is kind of like the golden standard of experiments. So for example, in a group of 100 volunteers, 50 were randomly assigned an experimental drug and the other 50 were assigned a placebo. Their blood pressure was measured once a week for the next 4 weeks. Since the volunteers don't know whether they got the actual drug or the placebo, but the researchers did, this would be an example of a single blind study. And of course, it makes sense for the volunteers not to know if they're getting the experimental drug or the placebo. If they knew they were getting the placebo, it wouldn't make sense to even call it a placebo. Now, in a police photo lineup, the officer shows a group of photos to a witness and asks the witness to identify the individual who committed the crime. Or like people, like I don't even know if they still do police lineups. I feel like they don't, but I have no idea. But since the officer is typically aware of who the suspect is, he or she may consciously or subconsciously influence the witness to choose a specific individual that he or she believes committed the crime. So there's a growing movement in law enforcement to move to a blind procedure in which the officer who shows the photos to the witness does not know who the suspect is. So that would be another example of a single blind situation. So again, a lot going on here. You've got single blind and double blind studies. You've got matched pair designs. You've got randomized block designs and a completely random design. As with everything in this unit, I think the more practice we do and the more exposure we have to this vocabulary, the more comfortable you will become with it.